Hi and welcome to this ORICtober video, a celebration of the Oric 1 computers from the early 80s in October 2021. The topic of the video today is going to be a little bit of a deeper dive into the serial attributes of the Oric, which is how the Oric handles changes in screen color and other effects as well. But I'm only going to be really talking about screen color effects today. In the last video, I showed some of the high-level features of the Oric, including a quick explanation about serial attributes, and I'm going to go into that a little bit more deeply today. Now, the observance amongst you might be thinking, this doesn't look like a normal Oric screen or a normal Oric program, and that would be correct. This is actually running a replacement ROM for the Oric, which contains my custom language called D-Flat. And D-Flat is a bit faster and easier to use than Oric Basic, so that's why I'm using it, but it doesn't affect anything I'm going to talk about because obviously the underlying hardware and how the display works is exactly the same. So whether you're using Oric Basic or whether you're using machine code or whether you're using D-Flat, what I'm talking about today applies because it's the same hardware underneath. And talking about hardware, just to show what I'm using today is actually the Oric Atmos, which I had acquired a while ago, but the keyboard was a little bit unreliable. But after talking to one of my Twitter friends, I reflowed all of the solder on the keyboard and it now seems to work great. So I'm going to be using the keyboard, the Oric Atmos today. And what's connected there to it is a simple breadboard with a EEPROM that contains the Oric D-Flat replacement ROM, and that's connected via this ribbon cable to the expansion bus of the Oric 1. So that's what I'm using. Let's get into the actual topic then. What you're seeing on the program screen here is two routines which are just going to help demonstrate serial attributes. And all they do is fill the screen, either the low resolution screen or the high resolution screen, with random color codes for the entire screen. And you'll see the purpose of that in a minute. But before I go into that, I want to just explain how serial attributes work. When the Oric display processor, the ULA, as we all keep calling it from now on, when the ULA starts displaying a row of graphic, the default color is white foreground and black background. So if you want anything other than that, you have to tell the ULA that what you would like is a different color, and then the ULA will use that color until it sees another code to change colors again, or it gets to the end of the row. So for example, on this screen we have cyan background and black foreground, and if we look at what's inside in the screen position at location 00, column and row 0, you see the code 22. Now cyan color code is 6, but you also have to set bit 4, so the value 16. So you get 6 plus 16, that's 22. And so that changes, instead of it being black background, immediately changes it to a cyan background in from column 0 onwards. And then if we look at what's in column 1 on that top row, you will see the code 0, because 0 is the code for black, and that's the code for foreground black. So that's why the ready prompt there is in black with cyan background. And in fact, if we were to look at what is on the next column, what you'll find is the code for R. So in column 2, row 0, 82 is the ASCII code for capital R. And basically that's how the Oric distinguishes between codes and displayable characters. If it's less than 32, and there are no ASCII displayable ASCII characters less than 32 on the Oric, then it interprets it as a code to do something. If it's 32 or more, then it displays the ASCII equivalent character from the character set that's been defined. So that's how it does it. So if I was to, for example, put at 3020 the code 65, hopefully many people know that's the capital A. So we can see there at 3020 we have capital A. What if I wanted that not to be cyan on red, but what if I wanted it to be, say, in red? Well, I can change the color immediately before the A and say I would like red, which is code 1. So if I hit that, you can see that the A has changed color. Well, what if I wanted to change the background color? Well, I can change the background color at that position. Maybe I want it in blue, so if I went 16 plus 4, which is 4 is the code for blue, you can see it's changed. But also, if you look carefully, the A has gone back to black. Why is that? Well, that's because in column 1 of that row I had already set the code 0, and the code 1 that I had earlier is gone, so it won't show. So actually I would have to change the code to red foreground, even to the left of the blue attribute change. And so now that I've made that change, you can see that I've actually got a red A on a blue background. However, I needed 2 characters to do that, and that's a bit of a bind if you consider that if you wanted A, B, C, all of them with a different foreground and background color, you would have to have 2 character gaps between them. Now there are some tricks, things called inverted colors, and inverted the inverse bit is set and it treats it slightly differently, but still it's generally a constraint. And if I show you how then this looks on the low resolution screen, if I was to put background colors into the whole of the low resolution text screen, you can see all of the different squares here that you can change the colors for. However, you can't put any text in here because the text requires displayable characters. If I start typing, what I'm actually doing is basically losing color information in place of text information. So that's a problem, and it's not as good as the Spectrum in that respect, because the Spectrum has a dedicated buffer to store information about the color or the effect that you want in a particular character position. So that's a a side effect of using serial attributes. It's very efficient because I'm only using 1120 bytes here to display the screen and to be able to change colors. So it kind of is efficient, and it's a little bit like how teletext and CFAX worked back in the day. But it's not great if you want a very, very colorful display. However, in the high resolution mode, things are a bit different. Firstly, the ULA still uses serial attributes, so that part is exactly the same. However, in high resolution mode, you have 40 columns with each of the 6 bits in each column addressable, so that gives you 240 pixels wide. But you also have 200 rows, which means you have far more attributes, 200 rows of attributes versus just 2080 low resolution mode. And on the Spectrum, you have a separate buffer which is only 24 rows worth of attributes. So in this sense, the Oric's got a bit more flexibility than the Spectrum. And if I use the high resolution example of filling the screen, then you'll see what I'm getting at. So all I'm doing here is filling every column with a different background color or a random background color, and for every row. And because there are 200 rows, you can see that it's much finer detail. So now there's a possibility to create more detail on the high resolution screen than you might be able to maybe on a Spectrum. And I'm not trying to diss the spectrum here, by the way. I'm just highlighting that although serial attributes are come with some big constraints, the advantage of low memory usage is there, of course, but also it can still help it can still be used in a clever way. And there's many people who have done some extremely clever things with it, which I won't be going into today. Now what I'm going to do is fill the high-res screen with random foreground colors, and it looks like it's filling it with black, but in reality what's going on here is that the foreground color is being changed, but there are no pixels to display, and therefore the default color being black in the background is all that's being shown. So the black background, which is the default, is being shown. There are no pixels being shown, so that's why it looks like it's all black. However, let's draw a line from the top left to the bottom right, and you can see we've got a very colourful line there. Let's draw a circle. At the centre of the screen, and maybe make it 70. And you can see there's quite a colourful circle there, and that gives you maybe a little bit more of an inkling to the fact that attributes can be a powerful way to manipulate the screen, both compact in memory but with some potential levels of detail that don't require lots of extra memory. On the TMS 9918, which you find on the MSX chip, for example, MSX computer, for example, that has also the ability to change every 8x1 position to a different color, which is great, but it takes an additional 6K of RAM. So you've got the display RAM of about 6K, and then you need another 6K for the color RAM, or the attribute RAM. So this is all being done in about in the same 240 by 200 pixel screen map. So that's one advantage of the Oric, and why I guess the Oric designers went down this route. It's still fiddly to make this work well, but some programmers have done a fantastic job on it, and I'll probably show some of that later on in the month. But we're over 12 minutes and heading towards 13 minutes, so if you're still watching this, then thank you very much, and hope you join in to the next video. Thank you. Bye.